So I'd like to thank the organizers for this workshop. It's lovely being here, and it's nice to hear all of these great talks. So I'll talk about a multifractal SLE-Caparo boundary spectrum, and the outline is somewhat. I'll start with the preliminaries, and then a very short introduction to just the necessary parts of imaginary geometry, and then I'll continue with telling you shortly about the martingales that we need to get the upper bound on the dimension, and then I go on with the 2-point estimate, which is the main part of the project in some sense. So first, SLE-Caparo processes are just a generalization of SLE-Kappa processes, where you keep track of additional points on the boundary and you assign them weights, which makes you either attract the curve or repel the curve. And a multifractal system, that's a system where the dynamics are not described by just one single exponent. So the fractal dimension is not enough to describe these dynamics, but instead we have a whole spectrum of exponents. And this has been studied in various forms before by Belyaev, Smirnov, Duplantier. They've all found the average spectrums. And then there are almost sure spectrums by Wiklund, Lawler, Gwynn, Miller, Sun, Alberts, and Binder. And so this is where we continue. And we continue with the boundary spectrum, but for SLE-Caparo, and it has been studied for ordinary SLE by Alberts, Binder, and Wiklund before. So what we want to think of is as take all of the points where your SLE-Caparo process hits at a certain angle. So now this doesn't make sense as these curves are very rough. So instead we consider this as the curve approaches the point x, we want the derivative of the conformal map to decay as a certain power of the distance. And this is actually, for a certain class of deterministic functions, this does correspond to actually approaching at a certain angle. But by the Koebe 1/4 theorem, we can actually see that this is the same thing as considering the decay of a harmonic measure from infinity of a certain set. So say that we have our point x here, and here's 0, so here comes our SLE-Caparo process. So that the derivative decays like that is the same thing as a Brownian motion started from infinity, properly normalized so that it's not something trivial, and the probability then of it hitting this region here between x and the right part of the curve, so okay, if it does something like this, then we just consider this part. So you can really view it as a hitting angle, as you see whether you hit this ball here or here will definitely affect the probability, because if your Brownian motion were to enter somewhere here, then most likely it would hit this part of the curve instead. So not go all the way there. And as I said, the SLE curves are very rough, so we cannot hope to have any up to constants estimates. But instead, we consider ourselves with this set V beta, where we get rid of all of these sub-exponential corrections. So that's, we just get the log and then 1/s. So the result we arrive at is that given our beta, this set has this dimension. So it's not a very nice expression, but if you're working with multifractal analysis, you know that there's always something like this showing up. And moreover, we can see that there is actually a typical behavior, for if we take the beta 0, then we actually get just the hitting dimension of the SLE-Caparo process. So we actually get the full Hausdorff dimension, So this is indeed the way that it should behave, looking at an average point that you hit. And we get the full result for kappa between 0 and 4, but we have not been able to use the duality arguments yet to describe it between 4 and 8. The dimension should be the same, but it's non-trivial to deduce it in the other range of kappas. So now I'll give you a very brief introduction to the tools that we need from imaginary geometry. So if you're interested, there's a 170-page something paper about it, which you can go read on archive. So the idea is that we want to couple a Gaussian free field with SLE curves, and then so that the SLE kappa rho arise as flow lines in the vector field e to the power of IH divided by kappa by chi. Chi depends on kappa, and we will say that the flow line that they are flow lines of H because it's shorter. So what we do is we take a Gaussian free field and fix some kappa between 0 and 4, and we have piecewise constant boundary data. Then we can couple the Gaussian free field with the SLE so that the flow lines of this SLE kappa rho from x to infinity is an SLE kappa rho curve. Well, the flow line starting from x is an SLE kappa rho curve from x to infinity. And the weights, the locations and the weights of the force points are decided by the boundary data of the Gaussian free field. And furthermore, if these curves collide, they merge and they never separate. So if we just start at x1 and x2, and at some point they merge into one curve. And this is very important in the construction of the two-point estimate. And furthermore, in this coupling, all these flow lines are almost surely determined by the Gaussian free field. And also, you can define this in any simply connected domain by just conformal mappings. So also using this coupling, you can see that, given a deterministic curve started at 0, you have a positive probability of not exiting the epsilon neighborhood of the deterministic curve until coming very close to the tip. And given some extra assumptions, mainly that the force points are outside of this small epsilon tube, and that this interval you want to hit is wider than the epsilon tube as well, then there's a positive probability bounded below by some constant that you will actually hit the interval before leaving the neighborhood. And furthermore, say that you have two different SLE kappa rho processes in two domains d and d tilde. If you take a subset U, so here you have your d and maybe your d tilde, and you take some subset U here, and you start your SLE curves here. If you stop them when they exit U, then they are absolutely continuous with respect to each other. And furthermore, given some mild assumptions on where the force points are located, you can see that the Radon-Nikodym derivative is bounded above and below by some constants. So these are the main tools needed. So now I'll just briefly go through what we do with the martingales. So first, this is how we get our SLE kappa rho process. We just defined it as the solution to this ODE, where our driver is the solution to this system of SDEs. This is basically just insert this drift part and you get your SLE kappa rho. And furthermore, we assume that rho is in this region so that you can hit the boundary. And this is shows that even if your kappa is less than 4, with this weight, you can hit the boundary. And then we just define some constants. We fix some UC, take some zeta in this range, and define these constants through mu c and zeta. We define the processes delta t and qt, and this is a local martingale putting them together with these exponents. And this local martingale is very convenient to use. So we weight the measure by it, and since this delta t is just a constant multiple of the conformal radius, it is proportional to the distance. So we can analyze the distance. So if we just keep track of this process delta t, then we keep track of the distance to the point x that we're looking at. And also qt has an invariant distribution, and since you're all probabilists, you know that makes it very easy to handle. Furthermore, there is a geometric interpretation of qt, which is very important as well. So given that you want to hit this point here x, your curve comes in like this. Qt is the ratio between the harmonic measure from infinity of this entire part here and this one. So it's this part, the harmonic measure of this part divided by the harmonic measure of the entire part. So it's bounded between 0 and 1. And this change of measure immediately gives us a 1-point estimate, which is sufficient for the upper bound of the dimension. And furthermore, this measure p concentrates on the event we're interested in. So in just a couple of pages, you can get the upper bound. So that's very convenient for us.
Could you show the martingale again?
Yes. So you have some conformal radius times ratio of harmonic measures, and then times the derivative. Okay. So the next thing we want to do is we want to utilize Frostman's lemma, which basically says that if we have a set A and we want to find a lower bound on the Hausdorff dimension of that set, we can find a measure with support contained in A, and if it is this energy integral is finite, then we know that the dimension is greater than or equal to the s that we have as the exponent here. So this is the standard method to prove the lower bounds on Hausdorff dimensions. So then what we want to do is we want to construct a set of perfect points, that is points which they form a subset of the set we're interested in, but there are many enough of them so that they actually carry the full Hausdorff dimension of the set. So the way that we do this is that we take a Gaussian free field in the upper half plane. So here 0, take minus lambda and lambda 1 plus raw boundary conditions, because then our flow line here is the SLE kappa raw curve with the force point here at 0 plus, which is the process we're interested in. And then these flow lines starting from other points are also SLE kappa raw curves, but we have 3 weights instead. And then we fix some very small constants, delta and epsilon. It's not important what they are. They're just very small. And we fix a sequence of points, just getting closer and closer to x. So x1 is of order epsilon from x, and xk is of distance of order epsilon to the power of k from x. and we just let sigma kx be the first time that your flow line, so say that your flow line here at x k, we can say, hits a ball of radius epsilon k plus 1. So it's the first time that you hit the next ball. And so the points that we're interested in, you'll see a picture showing this later, so it might be look a bit nasty. So first we want the event that a curve hits the next ball before leaving a bigger ball. And then we want this ratio of harmonic measures to be not too small. This is just a regularity assumption, so it will not chip away too much of our probability. It will just remove a constant amount. And then we want the correct behavior of the derivative as of the conformal maps. So the main point here is, okay, so we want to hit the next ball because we want to get close to the point, and we want the correct behavior. And this one is just there to be able to for us to make those geometric estimates. And next, given that we have sent these curves and they hit the next balls, we want the previous curve to merge with the next curve before exiting a bigger ball or the smaller ball. And also we have the regularity assumption that you should not get too close to the real line to the right of x. So the way that this looks is that, so we start a curve here, it goes and it hits this ball here, and then the next curve should also hit the next ball, and then we want this outer curve here to go in and hit and merge with this one. So if you've done any of these dimension results for random models, it's fairly standard that you want to get to some point where where what happens is independent or almost independent from each other. So in the like Wendelin and Scherban's paper, you have you can just see, okay, so what happens in these very small balls are basically independent, is independent, and then you have to just check what happens outside. And it's the same in the gasket dimension of CLE. But here we're not that happy because we cannot make it about real independence. But instead we have 2 points x, y, and we want to see that if we get close enough here, then all of these the curves at a certain rate will be almost independent instead. So how we do it here is just, so this is just a notation that this is the proper behavior from curve m plus 1 up until curve n. This is just the proper behavior up until the point n, and we want to know if this happens for every n. Do we have x in this set v beta? Well, yes we do, because given that, so if this is our outer curve, the SLE kappa rho, and this is the latest flow line is here in red. Okay, so let's make this ball a little bit smaller. I mean, the probability of going in here and hitting this part and just being able to hit this part here is about the same as the probability of going in and being allowed to hit all of this. So it's no real obstruction for us to look at just these events. I mean, if we view this multifractal dimension as a decay of harmonic measure. Oh yeah, as I said, this was by the Koebe 1/4 theorem. So I think kind of running out of time, but it's good. I have very few slides left. So, so just so that nobody will complain, this is the set of measures that I want to define, and this is the proposition that I want to have proven, or I have proven, but it's stated a little bit differently. Because you see, if you just plug this into the Postman lemma and you have this inequality, then it's fine. Then your integral is finite and everything is good. So the way that we do this is that we go through the scheme of JSON and how, and we want to separate these events at the right scale. So the point here is that if you have these
There's a brush behind you.
yeah, I probably should have used that. So if we just first consider, they should be very close. So if we just first take some ball around X, and then take some smaller ball, and start some curves living inside here. And we have a chain of curves here coming up to this point. Then these things live in different regions. So by the absolute continuity of the Gaussian free field, and these small extra assumptions that I didn't state properly, the Radon-Nicotium derivative between these curves here, given that this exists, is absolutely continuous with respect to these curves here, not given this information, and the Radon-Nicotium derivative is bounded above and below by some positive constant. So this basically lets us separate the points at a good scale and view them as independent, because everything, we only lose a constant amount of information there. And doing it in the same way here with y, we have to be a little bit careful, because we only have to pick smaller balls, but it will not affect our estimates. So then we have that what happens outside here and what happens here is approximately independent of what happens inside here. So that's how you get that part. And next, so given curves, given two curves, you want the probability of them merging to be proportional to a constant. And this is also fine, because given our regularity assumptions, we want this we want this part here to be not too much smaller than this entire part here, which means that this curve cannot hit too far down here, and also when mapping this back, we get some g of x and get 0 or f of x or whatever. It means that these force points here are mapped far away, and that means that you could just take your epsilon sausage around some point and hit this curve. So it basically guarantees that the mapping out function gives you big enough intervals to be able to use this one. So it gives you here that it's lower bounded by this constant. And for the last part, this is a bit nasty to do, but it relies on that if you know that they merge with up to constant probability and that you can separate them at the different scales, you only need to consider a curve at one scale. So you only need to be able to go within epsilon distance and see that you have this correct lower bound. And in the case of one force point, this is very simple. But these flow lines have they have 3 force points, so it's a bit nasty. But if this is xk and this over here is 0, then 0 is far away, so we can ignore this force point. And also these 2 points here, we want this one to stay because it's no problem, and this one we want to get rid of. So what we do is basically we want this to follow a simple curve. We map it back, then this force point goes away to the left, and we're stuck with only one force point. And then we're in the easy case, and we are done. So yeah, that's everything. Then you can just patch up with these curves with merging and separating, and you are done. And I hope I didn't go into too much technical details. So thanks for listening.
I think we talked about it before, but I didn't remember what the answer is, so I'll ask the question again.
Okay.
I mean, of course, the gas-free field is great because it works and the coupling things work. But so if you take for kappa larger than a third, and you take the construction of the kappa rows with the excursions plus loops of the SLE kappa rows, outer boundaries of the union of loops and CRD loops and is there a way to get also the 2-point, the down for the 2-point estimates, just in that case also the kappa larger than a third?
I did think of that, but
somehow it would depend on just the local behavior of the loops and the excursions there. And
yeah, I think it should be possible, but I haven't explored it because I mean this was more fruitful. But so I have no good answer. I think you should be able to do it, but it's not clear how.